Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, we're going to take a look at a case study from one of my clients. Hope you enjoy it.
Welcome to Complexity Made Simple and the latest case study, which is all about a combustion process, a furnace process, and the treatment of the waste gases. I've removed the company and the specific information about the process because this is proprietary to my client, but I have lots of clients who have furnace processes, combustion processes that are giving off waste gases that you have to control and treat. But this is just about the combustion process. It's about a furnace process, and it just makes a great point. We're just using basic principles here. We're making the laws of physics work to our advantage. And the problem is all about treating the waste gas. And you can see here, look, it talks about lime consumption. This is the thing that we're trying to control. So in order to control the waste gas, they choose to treat it with lime, and this keeps as much of the emissions of various gases down to an absolute minimum. So let's take a look. Here's the graph of the current performance, and now you can see, look, here's where they would like to be. There's the target. You can see that they're not under the target particularly often. This is a period from, look at this, this is 2015. What's the first date? 1st of December there, 2015, all the way through to the 8th of March 2016. So this is kind of a 3-month period at the start of the project. And just look at the graph. It is complete chaos. And let's just talk about this before we start. You cannot learn anything or do anything with a process when it is in complete chaos. Sometimes, look, we hit the target. It's a rare day at the office, but it does happen occasionally. Sometimes, wow, where are we going up here? We fly off the graph somewhere completely different. The other thing to say, of course, there are two lines on here because there are two lines. So there are two emission chimneys, I suppose, is the way to describe this. But essentially the same gas is going up the same chimneys. But look at this. Look at the amount of treatment that's being made. Look how far apart line 1 and line 2 can be on some days. Look at the gap here. Very rarely are they together like this. It's where they should be. It's the same flue gas. They should be treating it to the same level. This process, as it says at the bottom here, too much variation. The process is out of control. We sometimes think of process control to be all about making widgets, but the principles you're going to see relate to making widgets essentially, which is about getting process control. But it doesn't matter what the process is. The basic principles apply. The first thing you have to do is go from chaos to control, and from control to excellence. And that's what you're going to see in this project. Okay. Now this is a little slide. It's describing the chemistry. I talk about it being all about physics, but obviously there's an awful lot of chemistry in this particular process, and it's just something that's trying to explain this phrase here, this phrase stoichiometry, which is essentially what we're going to use as the main measure of the project and of success. And it's essentially, look, how much lime is used divided by how much lime was needed. And obviously, if that ratio hits 1, that's where we want to be, because exactly the right amount of chemical was needed for the right amount of flue gas. And you can see that what we're treating, look, is HCl and SO2. So that's the main measure of success. And I think the next graph is going to show you what the current stoichiometry looks like. And here it is. So 1 is where we want to be. Look, that's where we want to be. That's the same period, look, starting in December 2015, right the way through to the end of this project. And look where the designed experiment, this is an experiment here to find process knowledge to optimize the process. It's an optimization. It's an optimization experiment. Look where the results put them right where they want to be. Okay, but first of all, there is a period in the project of control. We need to take a little bit of the chaos out of this process, and you can see in this period, we haven't eliminated all the wild events. We're still getting a few. But you'll notice the green and the blue lines are stuck together. They are very much closer to one another than they were. This is a period where we are getting control of the process. This is where we are simply using the laws of physics to our advantage before we use an optimization experiment. So there's the way the project goes. And what are the simple laws of physics? Well, what we're going to use, of course, is the idea of simple process thinking. And we're going to use simple process thinking to get control of the process first of all. What does control mean? It means going to the input side of your process and simply fixing them. Okay, you simply fix the inputs. You agree a speed, a feed, a temperature, a setting, a maintenance policy, a procedure, and you make sure they happen as planned, on target, every time. It is a very simple thing to do, and it often revolves around procedures, methods, and equipment here. Maybe I can add in policies there as well. So obviously the methods will be things like settings, speeds, feeds, and temperatures. Equipment, this will be maintenance. Policies and procedures. Well, a policy could be you're trying to operate the process to its cheapest all the time. So what that might mean, it might mean that you drive the process in certain directions. That might be an agreed policy. So one of the reasons why you see the graph swinging around, someone's trying to fight the process, they're trying to find the cheapest settings all the time. But to be honest, you can only do that by fixing things. You can only get control of the process and get to cheapest by fixing things. So we're just going to do that, and that's what this project is going to do. First of all, we're going to get control of the process. So what we're doing here is we're identifying a list. So just to be clear, this is a list of inputs. All of these things on here, all of these categories on here are inputs. Where they are marked in green, that is an input that we have an agreed setting. We have a standard operating procedure. So to get green to say that we are in control of that input, we have to have a standard operating procedure. We have to be happy with it. In other words, it has to be nice and specific, meaningful. And finally, we have to use it. And if you get those 3 ticks in the box, then this variable will go green. Now you can see there are a number of red variables. Things like, look at this, the lime screw speed. That sounds like it might be important, doesn't it? What else have we got? There's a calibration routine somewhere here. The T-probe calibration frequency isn't under control. Again, that sounds important. So what we've done here is we've identified all the variables and whether they are in control or not. And then they've simply gone in and put some extra controls in place. And they've improved the control of this process. And this is just physics. If you do not get variability into your process, you will not get variability out of your process. And you cannot, let's get rid of that, you cannot take variability out by adjusting another variable. So you should not try. You should fix as many variables that are in your gift as possible. Yeah, so here's the physics working for you. Fix as many as possible. One of the things this means, it means stop fiddling, stop adjusting, stop trying to adjust the variability away. You can only make it worse if you do that. So that work's been done, and that's the period where they've got better control of the process. That's that period there. You can see it's taken them a while. It was the 1st of May to the 1st of August. So what's that? May, June, July, 3 months. That is a very typical period in order to get a process under control. 3 months. Now what we can do is we can go into the optimization phase. So let's just have a look what they achieved, by the way, in terms of the stoichiometry. We'll take a little look at the standard deviation. Look at the spread. So this is the variability in the data. You can see that before we started the work, we had a standard deviation of 0.37. After we've put the extra controls in place, how much has the variability gone down? Well, we've made the variability go down by 3 times. That's great work. That is a sign of process control. You will also notice, by the way, that the mean has gone down a little bit as well. If I just go back to the graph, you can kind of see that we're sort of sitting up here, and gradually the mean is beginning to sink down as we get control. Now that is very typical. You get good as you get consistent. Focus on consistency and good will happen. So that's line 1. Let's take a look at line 2. Similar thing, look. The mean is sliding down a little bit. Here we had a standard deviation of 0.3, and now we've got a standard deviation of 0.5. So we've taken 2 times the variability out of the process. That's fantastic work. Yeah, that's what you should be doing. Stability always comes first. So that now we've got some stability. There's just a summary of what's going on. Now what we can do is to take a look at the line control process and the combustion process, and we can identify some variables, some settings essentially, that may affect the way that lime is dosed into the system. So this is the control loop, and we are going to design a design of experiments. All right, so from this diagram, the experts have identified essentially 5 variables that they'd like to test. 5 variables. So let's take a look at these things. It's the HCl set point, variable number 1. It's the SO2 set point. It's the K1 constant, the K2, and the K3. Now they're almost like offsets that the equipment manufacturer uses to deal with all the slight differences in their equipment and processes when they install them, to get them all referenced to the same place. So there are various settings. They're called K1, 2, and 3. They are sort of constants or offsets. So we have 5 variables. Now let's just look at this thing. We're going to go, the HCl set point is going to go from 5 to 15. So there are 10 settings there. The SO2 set point is going to go from 25 to 75. There are 50 choices there. The K1 is going to go from 05 to 2. So what's that? That's 15 different places we could set this thing. Then we're going to go from 1 to 1.299. So how many settings would that be? It's approximately 30 places we could set that. And finally, there are 10 places at the end. If you multiply those values together, 10 times 50 times 15 times 30 times 10, what do we get? We get 2,250,000. 2,250,000 combinations. So if you try to optimize this, if you try to use skill to do this, the skilled person has to understand the best settings out of 2.25 million choices. That is just ridiculous. Now, by the way, the manufacturers of this plant have left them with optimized settings, so-called optimized settings. They've used their skill to do this. The client now has taken this piece of plant on full time, and they've said, you know what, we don't believe you. We're going to find our own best settings, and we're going to use something smart. We're going to use a designed experiment. So out of 2.25 million combinations, how many tests do you need to do this? You need just 16 trials. Yes, 16. That's all you need to do this. And by the way, something that's really important about this test, we are looking for the sweet spot. Look, we've got lime stoichiometry, we've got HCl emissions and SO2 emissions. So yes, we've got to get the ratio of lime usage to lime needed to be right, but also, of course, we've got to keep the emissions in the right place. So we are looking for a sweet spot. We're looking for a sweet spot in those three outputs. Imagine trying to do this as a skilled engineer. This is impossible to do off the top of your head. And yet this is how engineers think they can do it. It's not possible. Use an experiment, let the maths do the work, and the maths will find the best settings for you. So let's take a look at those 16 trials. So this is the process that we're going through. We're going to design an experiment, and we're going to take a look at the mathematics. So here's the 16 tests. So you can see, look, what we've done in each test, we've gone high and low in each column. High and low for the HCl set point, high and low for the SO2 set point, the K1, the K2, the K3, they've all gone high and low in a particular special pattern. This pattern is the fastest way to find out. Why would you use any other technique other than a designed experiment? This is the fastest way to find out, and it's only 16. Let's be clear. 16 tests out of 2.25 million tests you could pick. How efficient is that? It's the most fantastic technique to use. So let's have a look what the DOE is going to tell us. And obviously we're going to have, by the way, the yellow space here. This is where the data, this is where the test data goes. Obviously, we're going to have three of these. We're going to have the stoichiometry, we're going to have the HCl, and we're going to have the SO2. So there's going to be these tables, there's going to be times 3 sets of data, and then we're going to find the sweet spot. So here's the analysis. Each one of these, if you haven't seen one of these before, this is a mathematical model for stoichiometry. It's a mathematical model for the HCl down here, and it is a mathematical model for the CO2. How good are the models? Well, this one, brilliant actually. The way to read this, 85% of the movement in the data was caused by those 5 dials. When you look at the HCl, 71% of the movement in the data was caused by those 5 dials. And finally, 52%, not as good, but you've still got a good level of control over the SO2 there. These models are pretty good. Okay, so, and you can see that there's a comment on the bottom that from the analysis, one of the things they learned is that K1, if you set K1 to 0.5, it removes even more variability. Okay, removes more variability. So they've gone for even more control here. It's a fantastic thing to do. Great knowledge came out of this experiment. They are using it to their advantage. Using these models then, we are now going to ask the computer, what are the best settings? Please make a prediction out of the 2.5 million combinations that we didn't test. And what does that tell you? It tells you this is the sweet spot. Okay, so here are the requests, by the way, to the models. We want stoichiometry to be at a minimum, HCl to be less than 10 milligrams, SO2 to be less than 50 milligrams. That was the request, and the computer came back and said the sweet spot sits right here. 15, 63.7. The K1 is locked at 0.5. That was the one we just looked at to minimize standard deviation. K2 is at 1, K3 is at 0.5. And then what did they do? They did a 10-hour confirmation test to see how the process performed. And look what they achieved. Look where the stoichiometry's gone. It's gone from up here. I mean, it was up at 0.6, look. They were wasting 60% lime. They've got this thing now sitting dead on 1. By the way, just something to point out before we go off here. The equipment manufacturers, what did they say? They said these settings will never work. The equipment manufacturers were shown these settings, and they said, using our skill, we don't think these settings will work. Oh, really? Let's try them. So they went and dialed them in, and they got this performance. So you can see where the stoichiometry's gone, dead on 1. Look at the lime ratio, kilograms per ton. We were up here at 8. By the way, I think the target was sort of here. Look where they've driven this thing to. It is half what it used to be. That is just the most incredible process optimization, and so simple to do. You just go chaos to control. Then you design a DOE, and you go from control to excellence. This is the way Six Sigma works. People wonder what Six Sigma is. That's it right there. It is world-class process control. It is world-class technical problem solving, and that's the kind of thing you can achieve if you just follow simple laws of physics. Get the process under control, then use the best testing method and the best mathematics to find the best settings. How else would you do this? So just a little summary, of course, of what they achieved. And by the way, so all the money is around the lime usage, which is fantastic. So all of this is going great. The stoichiometry dropped to where it should be. But key point, the emissions stayed within limits at all times. We don't want to go biffing out loads of pollutants whilst we're saving money. That wouldn't be a smart thing to do at all. We found the sweet spot, the cheapest place to get the best process performance. And that's really what these tools and techniques are all about. And a little bit of a summary about how much money they've saved. We're sort of essentially talking about £100,000. Not a bad piece of work, especially when you consider, I think, that this particular company has 7 or 8 of these pieces of plant around the country, and therefore there's £1 million, I would say, roughly, to be saved if they implemented similar techniques across the country. So it's very easy to do. Chaos to control, control to excellence. This is Six Sigma in action. This is Six Sigma in action in a combustion process. If you're sitting out there with combustion processes, lots of chemistry, lots of chemicals, lots of heat, lots of lots of flue gases being given off, etc. And you're looking to find the sweet spot, whatever the sweet spot happens to be, whether it's the quality of the items, steel parts that you're heat treating, that type of thing, whether it's the quality of the items or whether it's the cost of the process. Using these techniques is the answer. It is the only answer because it's based on the laws of physics.
If you'd like to know more about any of the concepts covered in this video or any of the other concepts covered in my other tutorial videos, then here's my latest book, Drink Tea and Read the Paper. It covers everything you need to know about how to make sure that Six Sigma becomes world-class engineering in your company. Otherwise, if you'd like to get in touch with me, a little bit of help about Lean, a little bit of help with Six Sigma, please contact me on the email below.
About that topic, or indeed anything to do with Six Sigma or Lean for that matter, give me a call and I hope to hear from you soon.